So this is a topic that I've spent most of the past 1.5 years probably on. Yeah. So the course information for today, Project 4 is due April 18, and the grade school, I believe that's next Tuesday. And the grade school presentation check-in is on Sunday, so make sure you get it submitted. All right, so today's content, we're going to talk a bit about what is fuzzing, some techniques that are used in the fuzzing space nowadays, and I'm not going to talk about how to set up a fuzzer, but once you get to Project 5, the README is going to have very specific instructions on how you can set up a fuzzer and actually fuzz some real-world software. You're going to be using this testing technique against a 2013 version of ObjectDump, and you're going to find a bunch of bugs, and you're going to see how terrible software used to be. It's still pretty terrible, but how much worse it was back then, where you run a fuzzer out of the box against a binary like ObjectDump that is very heavily used, and it's going to find multiple crashes in the first 5 minutes. And this is also a technique that I would encourage you to look into using for your projects, because fuzzing is by far the easiest to set up out of all the analysis techniques we're going to be talking through today, at least at a basic level. You can go very advanced with it, but at a basic level, it's very easy to start with it, and it's extremely effective for what it does. All right, so let's start with the origin. So it was discovered in 1988 by a university class at Wisconsin, pretty much. The story is pretty much that a professor was teaching some class, and he was writing on his terminal at some point, doing some work, and some form of storm occurred and kind of messed up his signals, and some of his data got corrupted while he was typing, and then it ended up crashing a bunch of stuff on his system. So at this point, he thought, well, if my data getting randomly corrupted causes crashes of binaries on my system, maybe we could use that for testing binaries. So he gave his class as an assignment to write fuzzers, pretty much, very simple ones at the time, to test all the basic Linux utilities, be it ls, cat, all of these utilities that you've been using a bunch. And they basically, so I mentioned earlier, fuzzing is pretty much when you feed random data into a process and see if it behaves in weird ways, if it crashes. So I assume they just fed random data into it, and about 30% of the tested Linux utilities at the time just straight up crashed extremely quickly, even with those super basic fuzzing techniques students were assumingly doing at the time. They ended up publishing a paper in 1990 on it, and yeah, fuzzing they were describing was very dumb, very random, but it worked really well against these binaries that had previously only been tested by reading the code. Yeah, so getting a bit more modern, let's talk about AFL. So pretty much from 1990 until AFL, there was very little progress in the fuzzing space, in public fuzzing. People started writing better mutators, did some smarter mutations on the input instead of just completely randomly mutating it and stuff like that. But the actual industry did not start properly adopting fuzzing until AFL came out. AFL is what introduced coverage-guided fuzzing in the public tool. It was kind of known in theory before, but it was not widespread at all. So in 2014, AFL came out with that, and it's pretty much a fuzzer that is very easy to use, and it brought fuzzing back big time. Over the past 8 years since AFL's release, fuzzing has been massive in academia, thousands of papers published, it's been used in industry everywhere. Chrome is running, or the Google Chrome team is running a fuzzer against their Chrome browser 24/7 on thousands of cores, which has found over 7,000 to 38,000 bugs at this point in Chrome. So it's a very effective technique that people have been using very heavily since AFL kind of showed how good it can be to a degree. Let's talk a bit about the different types of fuzzers. So the first one is the simplest one that everyone can probably make sense of very easily. You just have some binary, you don't have any information about it, you just randomly send it data that maybe takes its input through standard in, maybe through some network packet parsing, whatever. You just send it data and hope something crashes. That's pretty much all you do. So at this point, the only control you have over the data, maybe you mutate it differently, maybe you have a better algorithm to decide which data you want to send it at what point. But it's a very straightforward way of fuzzing that works fairly well at times. Then there's gray box fuzzing. This is when you start applying instrumentation techniques to your target, which then leads to you improving the fuzzer. So this is where techniques like coverage-guided fuzzing comes in. This is you basically try to learn stuff about how your fuzzer is doing on your target while you're running the fuzzer. And this makes the fuzzing a lot smarter, a lot better, and we're going to talk about a lot of the techniques that gray box fuzzing implements later. And then there's white box fuzzing. This is, I don't know, the term is not heavily used overall, but it generally relies on having access to the source code of the target, and you basically just try to level up the analysis of gray box fuzzing to a whole other level, where adding other techniques like some lock execution, heavyweight analysis passes that try to make the fuzzing a lot smarter, which sounds really good in theory, but it ends up being a lot slower than the gray box fuzzing or the black box fuzzing, which makes it not that great in theory, in reality, oftentimes. So yeah, for this lecture, we're going to mostly talk about gray box fuzzing because that's the most interesting and most widely used of these. Any questions so far? All right. So let's talk about mutational versus grammar-based fuzzers. So we talked about the fuzzer basically just randomly mutates data and sends it to a target. Let's say you have some target. Let's say you're trying to fuzz the C compiler. You're trying to find bugs in C code. If you just randomly pass it a stream of bytes, you're very unlikely to find bugs nowadays. The C compiler is just gonna, if you remember, when we start drawing out our compiler pipeline last lecture, it starts at the token level, and at the token level, it's instantly going to realize, wait, there's some non-Unicode characters in here maybe. Let me reject that. This is not valid C code. It's just there are going to be a lot of very trivial things. It's going to instantly see that this cannot be valid C code. It's instantly going to stop the compilation. So you're not going to get very deep into the C code compiler's code base. So this kind of starts leading to some challenges. If you have something that takes highly structured input and very quickly realizes if it's the wrong input and just stops your fuzz case, how are you ever going to reach the code that's like deep in the background, the thing that handles like the complex parsing of your code? Because you want to actually get there. That's like where all the bugs lie, not like in the front end where it like starts tokenizing your code, for example. So this is when you start looking into a bit smarter ways to do your mutations. You don't just want to arbitrarily give it bytes. So first of these is mutational fuzzing. So for this, you take a corpus of input files and you do your mutations based on these input files. So let's say you're trying to parse a C compiler like GCC. You might take an initial corpus of, let's say, 100 different C files. You just download them from the internet, which is arbitrary C files, and then you do your mutations based on them. This then starts having a bit of a higher likelihood of succeeding because you're much more likely to start corrupting things that don't immediately stop the compilation because you do have this valid C code, but you're still corrupting things that might, like somewhere in the background, cause an issue. Yeah, so pretty much the idea with that is you fuzz your target, you mutate stuff, and if something crashes, you save off the input file, and then you can manually inspect it later what actually caused the crash. And then there's grammar-based fuzzing. So when you're dealing with compilers, this is what you would actually do. In this type of mutational fuzzing is what you get out of the box with like AFL and all these tools. It's not as effective for compilers, so it's probably a poor example that I brought up there. But let's say you're dealing with like a PDF parser, like a couple of the groups here are. If you're just randomly giving it random bytes, it's probably not going to get very far. It's not going to have like the correct headers for a PDF file. It's just not going to make much progress. But if you take initial input of 100 PDF files and you just mutate those PDF files instead and give it the PDF files to it, you're going to get much further. But if you're dealing with very highly structured input that is much more structured than PDF files, like C compiler, for example, you look at grammar-based fuzzing instead. For this, this usually starts becoming necessary if you have an application that deals with a very strict input format, like compilers do. So instead of dealing with a corpus with this, you generate code based on a grammar. So you've all dealt with context-free grammars, right? In 250, I believe, probably, where you set up some grammar, and that basically defines what kind of inputs are allowed. Let me open up an example for that real quick. All right, so this is a very simple grammar in this case for a run-on sentence in this case. Here we just start of the grammar, which is the run-on sentence. And a run-on sentence, you say, is basically a combination of either a sentence or a sentence with a white space, conjunction, white space, and another run-on sentence. Like this, you can basically recursively define your grammar. So you can then give this to a grammar generator that then starts walking this grammar tree, and then recursively generates inputs that are valid based on this grammar. So in this case, it might generate some sentences like, let's see here, a sentence is a subject, white space, verb, white space, fruitless. So it could be a subject, let's choose I. It could be next, so we have a subject, I, then a verb, say eat, and then some form of, then a fruit, conjunction, like apples and bananas, whatever. And since this is a recursive structure, this could go on for a much longer sentence, and this is basically how all these grammars are defined. So you can define a grammar like this to basically model the entirety of the C language syntax, and then it's basically going to generate some pretty randomized C programs for you that are always syntactically valid. So you're going to get some really weird C programs based on this recursive definitions, all of which are pretty much valid though. This means that they're going to get much deeper into the compiler's code base and are much more likely to find some of these deeper bugs. This is, for example, a technique that is very heavily used when fuzzing the JavaScript engine of browsers.
An example of stuff I've used in real world for this was looking at compression systems. If you want to get deep into the compression system, usually you want something that's not compressible, right? And that's something with high entropy or seemingly random data. So you can create grammars that, based off the previous text, will choose something that's not similar, and then it will keep going down the if-else trees and all the different compression algorithms. So you can do things like that too.
250 finally coming in useful.
Yeah.
That's how I felt when I learned that, at least. Any questions on this?
Use cases, anything? Industry?
Yeah.
I'm just thinking about this in terms of my project, because it's maybe a grammar-based fuzzer. So if you had say you wanted to define maybe a set of a couple functions on the whole grammar of the language, would that be possible?
Yeah, of course.
So you could limit it, so it could maybe only call the functions you want, and then would you have to define parameters and stuff for that as well with grammar-based fuzzing for certain functions?
With this, you're not defining the functions you call in your target, but rather just the input you generate, and then you decide how you pass the input to your target.
Okay.
So if you only want to fuzz, let's say your target has an HTTP parser, JS parser, whatever, you might just want to focus on one of these parts, so you might write an HTTP grammar, and then only pass that to the HTTP parser.
Okay.
So that's two different aspects, kind of. Although I would say yours kind of takes binary packets, right? The 5M client. Or what kind of format are your packets in general?
I don't know about the packets, but if we were to fuzz the script generation part, it would just literally take in Lua files and then call the C hooks. So we'd have to define a grammar that contained all the Lua to C functions, and then basically it would fuzz those.
So you could set a Lua grammar that also includes these special functions that are in your client to call those instead as well?
Something like that, but I would probably try to avoid most of the Lua functions, so because I feel that's
something like that is definitely possible.
Okay, that's interesting.
For other groups, potentially, if you want to fuzz something that takes highly structured data, so not something like a PDF parser, for something like that, or LaTeX parser, whatever that some groups have. LaTeX is actually another thing where a grammar-based fuzzer would work very well. But if you're doing with PDF, for example, the simple mutation stuff is perfectly fine. But let's say you're dealing with web packets. Those are potentially a lot more structured. You might have a length field. You might have some fields that need to be a very specific way for it to get somewhere. And it might be simple enough format that you can manually define all these structures. There's some stuff that is worth looking into, kind of protobuf-based fuzzing. Protobuf's a project by Google that basically lets you define the structures and then serialize them between different programming languages and stuff. That's something you could use to set up different data structures and then serialize them in a way where you can control which parts of the data get mutated and stuff like that in very interesting ways, which can be very effective for fuzzing packets and stuff like that. Right. It's not going to be on the slides or on your projects. That's something you can look in your own time after this if you're interested, but yeah. Any other questions? Here's a slide that will make Eamon happy. Web fuzzing. So in this class, we're dealing with binaries, so that's what you're going to be doing on your projects, fuzzing binaries. It is by far the more interesting thing of these two, but you can also fuzz websites. Don't do this because this quickly becomes illegal if you're sending thousands of requests to some arbitrary website. So don't do this against like websites on the internet. You can like host your own website and try it out against it if you're interested. But when you're dealing with websites, there are like certain other class of vulnerabilities. So we're dealing with memory corruptions. When you're dealing with web-based stuff, like other vulnerability class like XSS bugs or SQL injections, things you might have heard of. And that type of fuzzing is often done by taking, for example, a word list that contains a bunch of payloads that might corrupt some SQL requests or XSS requests. And then you basically use some form of web fuzzer like GoBuster or Burp Intruder or whatever, and go through these word lists and just pass them into like some fields on the websites that take input, and you see if one of them might cause like some errors on the site. So this is a fun thing. A technique that also applies to websites, but web fuzzing is in general very simple and very boring. So don't look into it, go for it, but it's not. Yeah, there's not much to it. But yeah. Anyone have questions on that?
Are those tools like available then?
Yeah.
This is okay. I thought if it was like semi-illegal then.
No. So these are usually used by, for example, if you work as a penetration tester and a company hires you to penetration test their network. You like sign a contract that gives you legal rights to like test their website, and then you might like run a tool like this to test for like some easy to find bugs. Or if you're like dealing with like training platforms, that's where most people like initially learn them, like Hack the Box, or like a training platform where you learn to hack websites. There you are going to get exposed to like tools like this that you can run to fuzz websites. If you just take those tools and run them against the arbitrary website, that's when you might get in trouble.
How exactly does sending a bunch of requests into a website illegal?
If you do it with malicious intent and actually find something, then it can, like if you end up crashing their website by doing something with malicious intent, like fuzzing their website, then that is illegal.
Even if you don't do anything bad, there's laws. It's like CFAA, I think it is, where it's like purely intent-based. Like even if you just mess around and send a request that does nothing, you can still get like sued for it.
So when you're dealing with websites that don't belong to you, usually just don't. Unless there are bug bounty programs where companies like say this type of website is in scope against these types of bugs, and that might then give you permission to test the websites against those types of bugs. So you could like go on, like create an account on one of these bug bounty website platforms, see which companies might have their websites in scope there, and that might be a target you can look at. But in general, don't just start hitting arbitrary websites with buzzers or any form of security testing. With binaries, it's a bit different. We're dealing with binaries here, things you can download and test on your own local system without affecting any other users. There's still like sometimes restriction, like if you are allowed to reverse engineer stuff, depending on like what country you're in, stuff like that. So I think games have like some legality things, or things you might be allowed to reverse engineer or not. Like creating custom game clients, I think has like some issues there. So like, there are always laws, but when you're dealing with binaries, it's usually the laws are usually a lot more on your side, where if it's on your system, it doesn't affect anyone else, and you're not like doing this for like monetary value by like releasing a page alternative game client or whatever, you're usually on the fine side.
Also with web fuzzing, most of the libraries and backends they use, like take Node for example, you have a bunch of Node libraries you can download yourself and try on your computer. So if you want to if you know a website runs a certain library, you can fuzz that on your own computer.
Yeah. All right. Also, obviously, none of us are lawyers, so if you actually want to do something, obviously, check if it's actually legal. But yeah, any questions so far, though?
I want to make one statement. So what's the saying, like when you have a hammer, everything looks like a nail? That's fuzzing for security. Like in industry, people will be like, well, I've reversed this for 3 months and gone nowhere. Or they do it day one. And they're just like, I'm just going to throw the company's supercomputer at it for like a week, run like 1,000 instances and fuzz it. And if it finds something, I'll report it or I'll exploit it. And if not, new project.
Yeah, so there's kind of two types of people that do fuzzing. There's that one. We kind of just like use fuzzing as like just like offload some of the manual work. There's also a more involved process where you kind of reverse engineer next to the fuzzer, where you kind of, I think I'm going to explain that more at the end of the lecture. Actually, no, it's fine. So let's say you're running a fuzzer against a software. You could just set it up and like run it against one of the input functions. Let's say you're fuzzing something that takes like input from 50 sources. You're just like running it with an arbitrary byte mutator against like one input function. That's very low effort, might still work because fuzzing can be very effective, but if it's a hardened target that has been security tested before in the past, you're not going to get very far. So what can you do instead? So you might add some form of statistics and instrumentation tracking to your fuzzer, and then you start running it against a target, and you see where the fuzzer gets stuck. You might see, okay, it's hitting this function, but it's never hitting this function. And then you might assist it in your reverse engineering. You might look at, okay, what is causing it to always skip this function, but only hit this other code? So like the one that hasn't been hit before, people that have previously fuzzed it might not have looked there before. So then you might reverse engineer it and figure out what's stopping the fuzzer from getting there, and then you give the fuzzer like a manual push, like adding more input files to it that can like get it to that point that's like it's not reaching by default. Or another thing that is usually for hard targets, like easily a 3 to 4 month process of full-time work, is properly harnessing a target. So let's say you deal with a target that takes its input from a bunch of different things. It can take web requests, it can take GET requests, posts, can like take data packets, and can get input from a bunch of different things. So then you need to write a harness for the fuzzer that lets it actually send its input to all these different things. Like you might implement a grammar for some of those. Like there's a lot of manual work that can go into it. But as Steven said, you can also just run a dumb fuzzer on a lot of cores and hope something happens. So it's kind of two different approaches. Usually when you go into industry, the art people, there's kind of this split where some people prefer the very manual approach where you read a bunch of code, where you debug the code. And there are others that kind of prefer the automated approach where you maybe write automation passes using your decompiler, where you write fuzzer and harnesses for certain things, and you start to automate a lot of the things. They're two different groups. Both can be very effective. You just got to kind of like see what you prefer, what you want to work with. Yep. Any questions? All right. Let's talk about the first improvement to fuzzing, that being address sanitization. Who here has dealt with the address sanitizer before? Okay. Is it not the 377 or 230?
Josh talks about it in 230, but that's it.
Cool. Okay, so address sanitizer is a tool that I believe was released by Google in like, was it 2000? I'm not sure when. A while ago, not forever long, but it's been a while now. And this basically instruments your binary to, so the fuzzer has many downsides. Like one major downside is that in general can only find crashes. So if you're maybe giving an input that maybe triggers some heap bug, like a use after free, but as you saw in the heap stuff we were talking about, a use after free is not instantly going to crash your program. It's going to corrupt some memory, it might corrupt the pointer, but it's not instantly going to crash it. So that's a bug a fuzzer would then potentially struggle to find, because you're corrupting some memory, but you're not crashing the program, so you don't know it's corrupting some memory. So this is where address sanitizer comes in. This is something that you can compile your code with. Clang supports it, GCC probably supports it too. Basically add it as a compiler flag, and when it's compiling your code, it adds address sanitizer to it. And it's going to alert you on many bugs that wouldn't crash by default. So what address sanitizer is going to do, let's say you make a heap allocation, and then right before and right after the allocation, it's going to insert like some guard pages. And then when you have a heap bug that goes outside of your allocated space and like writes into the guard page, address sanitizer is going to realize that and going to trigger a crash for you. So then you know, like this bug that would have usually just maybe corrupted a size field that wouldn't immediately crash, it's now going to write into this guard field and immediately crash. Similar to like the heap allocator, address sanitizer is going to replace that with an allocator that once you free something, it's going to properly free it and make sure that if you try writing to it after it's been freed, it's also going to trigger a crash like this. Similar to a lot of stack buffer overflows. So address sanitizer is like a compile time flag you can add to your code. So when you're testing it, it's going to find crashes that you wouldn't find otherwise. In certain ways, it behaves like logwriting in that sense, where you kind of just instrument your memory to find things that you wouldn't otherwise. Yeah, so there are different ways to do address sanitization. Usually it's done using compile time stuff, but you can also do it using emulation. So when you're running your code in emulator, you could instrument all of your memory loads and writes to kind of be aware of your memory layout and kind of apply this ASAN to some of your code, like by replacing you could, for example, hook the malloc and free implementations of your code and replace them with secure mallocs and frees that trigger false and double frees. And that could be then caught by an emulation-based buzzer as well. So you don't always need source code to add address sanitizer, but it's generally a lot easier if you do have source code. Any questions on this? And this is something that exists by default on your systems, on your compilers. So this is something you can very easily test if you have GCC, playing whatever, like your C compiler. You can compile some C code, or even like the example project, like the demo binary I gave you for each stuff. So I compile it, try to trigger some of those bugs, and then try to trigger them again after compiling with address sanitizer. It's going to give you a nice printout of like which bytes of memory you corrupted, and it's going to be mad at you. So yeah. Questions on this? Yeah.
How much does this affect like performance and binary size?
A lot. Forgot the exact numbers, but yeah, it seems to be about 2x on performance and 2x on memory. It's about 2x performance and memory, at least according to Android stocks, which seems to about line up with what I was expecting. But yeah, so there is a heavy performance penalty. So you wouldn't generally run it on your production apps. But when you're running your unit tests, when you're maybe fuzzing your code in your CI pipeline for a while, you do want to have address sanitizer enabled. And if you're looking at big companies like Google or whatever, when they fuzz their code, like Chrome, that's like the browser I'm most familiar with, they always have address sanitizer enabled because just a lot more, it makes a lot of these testing techniques a lot more effective at actually finding bugs. Any other questions? Okay. Let's move on to coverage tracking. So let's look at this code here. We have a function, it takes in a character pointer, and then it checks if x of 0 is equal to 0x41, if x of 1 is 0x42. So you have a 4-byte sequence here to be an exact value. Let's say you're running a dump buzzer that just gives it, let's say 4 bytes. Let's say we know that it takes exactly 4 bytes, that's what it's expecting, and you want to get to this success message. Maybe there's a bug here, who knows? If you completely arbitrarily randomizing this 4-byte value, there are about 2 to the power 32 possible inputs you could give it, and actually finding these 4 specific bytes, the A, B, C, D, to trigger this is very unlikely. Does anyone maybe have an idea on how you could make this smarter so it could actually find this? Yeah.
Like you can check if it passes each if case and then just set those bytes for the rest of the fuzzing.
Yeah, that's a good idea. So after each of these checks, we pass the first one, we say, okay, we realize that having the first byte set to 0x41 gets us somewhere that we haven't been before. So let's give that to the fuzzer for the future. And then suddenly we brute force them byte by byte. So instead of 2 to the power of 33, we have 2 to the power of 8 times 4 that we need to hit, and that's a lot easier. That's something we can brute force in a millisecond. Well, this is something we can brute force in a very, very long time, especially when the inputs start getting bigger. So this is a technique which mentioned is called coverage tracking. With this, you're basically measuring the code coverage that your fuzzer is achieving. So when you run this, your fuzzer would say, oh, let's say you're running this program with an arbitrary function. Once it finds an input that passes this, the fuzzer says, okay, I've never seen this code before. This is the first time I've gotten here. let me save this input that got me here. So let's say you start your fuzzing run off with one input. Let's say you maybe initialize your input to ZZZZ. So you're going to run it for a while, and eventually it finds an input that passes the first check. If you're only corrupting a single byte at a time, maybe the input that passes would just be AZZZ. And then you add that to your corpus. So now you have 2 files in your corpus, and half of the fuzz cases you might be running the first one, and half the fuzz cases you might be running the second one. So now at some point, the second one, which already passed the first check, is going to also find the correct second byte. Or, didn't want to edit this one. So you keep running with this fuzzer, you randomly mutate those 4 characters, and eventually you find a fuzz case that is A, B, Z, Z. And that passed the second check, you save that one off too, now you have a corpus of size 3. You keep running your fuzzer with all 3 of these, and you keep going like that. And eventually you're going to find this, and can you see why brute forcing it in that way, where you only need to find 1 character at a time, is much easier than fuzzing it in a way where you need to brute force all 4 characters at the same time. So this is a technique that basically AFL brought to the board in 2014 when released. It was a technique that was already known, and I think there were fuzzers that existed using it, I think since about 2012. But all of them were kind of more academia projects, hard to use. So it didn't really gain popularity. Fuzzing wasn't really interesting in the industry's eyes until AFL became a thing, and it implemented that. There's actually a really fun video or GIF for that based on AFL, where they start AFL with like a random stream of bytes as their initial corpus, and then they run it against like some image parser. And over time, as AFL, through this coverage tracking, it eventually like keeps mutating the inputs in ways that gets further through the program. And eventually, while running against that image parser, AFL like emits like valid PNG files that you can like there's like a GIF somewhere that I don't have the link to right now. Maybe you can find it real quick. Right, you can basically see it like start from like nothing, and then over time it like grows into an actual PNG file pretty much that like actually explores like input state of this image generator or of this like PNG parser. That's like was a really interesting demo where you basically went from nothing to generating a valid image, even though you knew nothing about the input format that this thing was expecting. There have also been like more recent things where someone had a fuzzer solve Mario, or win Mario, where it was just playing the game, and then whenever Mario got further, through like some input action, it would save that input and keep going. And then by running it for like a while, you would eventually have a fuzzer that like played the entire Mario by just mashing random buttons.
I don't know if this is like out of scope, but has anyone tried to like apply like reinforcement learning or like genetic algorithms?
Yes. A lot. But TLDR, it's way too slow. So fuzzing, you want to go fast. You want to have thousands of cases per second. Optimally, you'd like millions, but if you're using tools like AFL, you usually get thousands. If you try to do reinforced learning, there are for like various applications. Some try to make the mutator smarter by adding reinforced learning. Some try to, let's say, while you're growing this corpus, you see that maybe some of these find new inputs more often than others. So there have been papers that try to use reinforced learning to like better make decisions which one of these cases to prioritize. There's been a good bit of research in that, and some, at least in their papers, they claim that they have these certain types of improvements and whatever. In reality, it kind of always comes down to it cannot compete with tools like AFL and performance, so it's not worth doing because it doesn't produce better results. But yeah, there is research on it. If you look at some papers, you can find a lot about it. And the papers are going to make some very convincing arguments, and then you look at what industry does, and no one uses it. It's like the papers set up like their test cases in ways where this does benefit it, and then when you actually run it against proper stuff, it's just not going to perform. It's going to run like several orders of magnitude slower, and it's not getting anywhere.
Does it run with every file in the corpus, every input, or does it just run it?
One file per input, or
Okay.
per like run of the target.
But it runs it with all of the files, like.
Yeah, you might have like some round robin scheduler, like you might have heard from like your operating systems class. It's like first it's running with this one, then with this one, then with this one, and it's like loops around. It's like runs the target with the 3 files in loop. Or you like implement a bit more of an advanced scheduler, which we're going to be talking about later a bit, that assigns weights on these, for examples. for example, let's say that it says this one just found me new coverage, and this one I've run for like 10,000 times, and it's only found me new coverage once, like 5,000 cases ago. So this one might be getting less interesting, while this one just got new coverage. This one may be very interesting. So maybe it assigns a higher weight to this one. Say this one maybe has a weight of 9, this one has a weight of 1, and maybe it runs this one 9 times in a row, while it only runs this one once. So there are like some ways to like schedule them, like different ways. But yeah, you can just like run the fuzzer with one input, and then you decide on the next input in one way or another. Were you able to find anything on that?
Yeah, I can put in campus wire.
You want to send me the link maybe? I can put it up. If it's like the video.
It's not the video, but I found something that it's like a blog post.
Okay. Let me scroll through that real quick.
It also says they've written valid bash scripts, GIFs, ELF files,
Oh yeah, this is
RE executables.
This is actually the blog of like the original AFL dev. But yeah, this is kind of what this blog post in specific, or like at least like this kind of demo, really impressed people. Where he started out the fuzzer with like nothing. So let's see. So like the input he initially gave the fuzzer was just echoing the hello string into a file. And then he runs this AFL fuzzer here using this one input, which is the hello string, against like DJPEG, which is like some form of image parsing. And he runs that for a while, and initially all the test cases are going to fail because like it's just not an image. But then he keeps running it. As you can see, over time, the fuzzer, through this type of coverage tracking, it realizes that maybe if I add an image header to it, it's going to get further in. So that eventually it has like this image header in it. And the fuzzer does nothing smart, it just does these dumb mutations like bit flips, spike replacements, and it does this type of coverage tracking where it sees this cover. If I have these bytes in it, it's doing well, so I add this to my corpus. And over time, you can see how it just generates a bunch of valid images from this initial hello string. And this at the time really impressed a lot of people and brought fuzzing back big time in academia and industry. And people did a lot of very interesting things with it. Okay. Any questions on this? Let's talk about some different ways of doing this coverage tracking. So we simplify it, we just say that the compiler realizes when it's like executing some branch it hasn't hit before. But how does the compiler actually know that? So there are a few different ways to do it. So the first collection method of that is just to instrument it at compile time. So assuming you have this program, your compiler might, for example, insert after every single branch or whatever, it can insert like an extra instruction here or a line of code that communicates to the fuzzer that I just hit new coverage. So this could be like some form of shared, assuming your like fuzzer is like running this process like a child process or whatever, you might be able to set up some shared memory between the fuzzer and the process. And the compiler, or like you have some compiler pass that whenever you have like some branch or some control flow, it adds like an extra check in here that writes some command to this shared memory that lets the fuzzer know I just found new coverage. That's the first way. This is usually currently this is usually done using LLVM, where there's like an LLVM pass that the AFL people wrote at some point that does this pretty much. When the fuzzer launched like different threads with like running the fuzz case, it sets up like shared memory between them. And then whenever like a branch is hit that you want to instrument using this coverage, it like writes to the shared memory to let the fuzzer know. And there's a different way called when you're dealing with Intel Pin or Intel PT. Intel PTs, they're actually something entirely different, so I probably shouldn't have put them together. Let's start with Intel PT. This is a hardware feature on your computers. Your computers meaning you would need very new Intel devices for this, but in theory it could be on your computers. It's definitely not on mine. But it's a hardware feature that you can pretty much use that traces whatever's running on your system. So using Intel PT, you can basically just enable it, and then it's going to give it some memory set up for it, and then whenever a branch is hit, it just like writes to this memory and records what it's doing on like a hardware, on like an architecture level. So this is not like some compiler pass, like some emulation where it's actually modifying the code. The CPU just like has some hardware features in it that whenever like a branch is being executed, it like tracks it. This is a very modern feature that some fuzzers use. Not all of them. Compile time instrumentation, funnily enough, is faster than Intel PT. Not because Intel PT at runtime is that expensive. It's actually the CPU does it pretty fast. I think it has about like 10 to 20% performance overhead maybe. But the issue is in parsing it. So the way it does this type of format is it pretty much just like whenever a branch occurs, it writes like a 1 to it, and when a branch is not taken, it writes like a 0 to it, for example. Like it has a very simple format. It doesn't like tell you the addresses that it's branching at. It doesn't tell you like anything specific. It just tells you branch taken, branch not taken. So what you as the fuzzer developer need to do is then have like your binary, have like a control flow graph for your binary, and while you're fuzzing, basically go through this graph and compare it with like the Intel PT information. So like see if you just found new coverage or if it's just like old stuff you've already hit before. So like this parsing of Intel PT then gets very expensive, so it has a bigger performance overhead over compile time instrumentation, but it's still fairly fast. You usually have like about a 1.5 to 1.7 overhead, 5 overhead with it, but it's not terrible. You have like overhead, but it's usable for fuzzing. Intel Pin, this is something entirely different. This is software, it's not hardware anymore. This is a tool we're actually going to be using in class this semester in a later lecture, probably pretty soon, I think, actually. Might even be next lecture, not sure. But this is a software tool pretty much that when you can just call it from Linux, you can install it. Pretty sure it only supports x86, but you can call /pin, provided like some pin tool option. Pin tools are like the scripts you write for a pin that tell it what to do, and then you run your binary. Let's say you want to run an LS. And pin tools are basically binaries that lets you instrument stuff at runtime. So you could have like some closed source binary that you don't have source with, but with a pin tool you can say, whenever this binary hits a new basic block, print out the block's address or whatever. So this is something that like runs, I'm going to explain the exact specifics of how it does that because it's pretty interesting. Once again, gets into compiler theory, it's very prevalent. But that's how pin does it. This is a lot slower. It has like about a 2x overhead in general, I believe. Or does it? Actually, I'm not sure how much of an overhead it has, but it's slower than Intel PT in general, and it's not really used for fuzzing. Similar techniques have been used in fuzzing. There's a fuzzer called WinAFL. It uses a library called Dynamorio for its coverage tracking, and now it operates very similar to PIN. I'm not going to go deeper into that now. We're going to describe how exactly PIN works in a future lecture. And the third way, which is by far the easiest, when you're running your child process at random intervals, you just ask the process, hey, what address are you at right now? And it's just going to tell you, and based on that, you like record if you're like at a new location or not. This obviously is not deterministic, so it's not perfect. But if you're running your target fast enough, this has 0 overhead, pretty much. So it works very fast, and it's not perfect, but you do get coverage information out of it without actually having to instrument your target just by like asking it where it is. This is very simple to implement, very simple to do. It's very low overhead, but it's kind of worse than the other two because you might miss a lot of new coverage. Any questions on these collection methods? All right, so let's talk about the different types of coverage that exists. Or I guess.
There's 20 seconds left in class.
Yeah. Yeah, let's leave it at that. Any questions on this? Cool. We'll finish this next lecture.
Our lecture, next lecture?
Or your next lecture, we'll see. Whatever we do. So for today's lecture, we're going to finish the fuzzing stuff we started talking about last lecture. And then we're going to talk about, if we still have time, some other stuff that wasn't officially on the syllabus, but I think would be fun to cover. We got through this entire slide last lecture, right? I believe. I guess no, I think we talked about the upper ones, not the lower, not the bottom one. Does anyone want to give a go to like summarizing what fuzzing is and what we've kind of talked about in terms of fuzzing so far?
Fuzzing is like you generate like kind of pseudo-random input based on a set of like previously defined formats, and then you see how far into program execution they get you, and into what functions, how much coverage and stuff.
Yeah, so all of which is correct, just you kind of specialized a bit. So there doesn't have to be a format, you can just do it completely randomly, but one of the options is to define like a grammar for grammar-based fuzzing, for example. So yeah, that was correct. And yeah, one of the goals is to kind of see how far you can get through the program through coverage, as you mentioned. Not because getting coverage is your end goal, but because if you can explore a bigger state of the program, you have a much better shot at finding some bug that's nested deep in the program. So your end goal is not to get a crash out of the program or find some form of bug through fuzzing. We talked about admin sanitization in terms of that, where it's a compiler pass that modifies your target in a way where even small out-of-bounds access are going to crash the target, so you can find more bugs that you otherwise couldn't be finding. And now we've gotten to coverage. Does anyone want to summarize what exactly coverage is and how it can be achieved?
Is coverage kind of like what branches of program execution you're actually getting to when you give your random input?
Yes, exactly. So last lecture we started talking about a few ways of how you can collect the coverage. It can be through compile time instrumentation, where while you're compiling the target, you add some extra checks in there that add the coverage. This can be through tools like Intel PT or Intel Pin. Or another one is very simple, you just randomly request a location, you just launch the target as a child process, and every now and then you just look into the child's memory process, where are you right now, and you record that as a coverage location. So there are a couple of different types of coverage you can be collecting. There are many more, but these are the most popular. The first one is block coverage. So let's say you have a CFG here, say maybe it looks like this. Your program, it's like a control flow graph of it. So with block coverage, this is the most straightforward one pretty much. You only track your coverage in terms of which blocks you fit. So if you fit this block, you record a coverage event. If you fit this block, you record a coverage event. So let's modify this a little bit and make the example better later. All right, let's make this our graph. So with block coverage, you only record which blocks have been hit. So you say, I just hit this block. If you've never hit it before, this is a new coverage event. I just hit this block. I've never hit this before. This is a new coverage event, and so on. Then there's edge coverage. With edge coverage, you cover which edges you've hit. So this would be an edge, like all of these edges that connect the nodes of the graph. So the advantage of edge coverage is, so with block coverage, you could say, I've hit this, this, and this. But then let's say your program takes this path. You hit this block and then this block. Since you've already hit this block before, this would not register new coverage on this, even though this is a new edge. So with edge coverage, you can get it a bit more fine-grained and determine a bit better if you've actually hit something before. For example, if it's a very popular, let's say you're trying to get coverage on like a mem copy, how often you hit a mem copy. With block coverage, you'd only know, okay, I just hit mem copy. With edge coverage, you can get new coverage whenever you hit this mem copy from like a different function. And that could also be relevant for your fuzzer. And there are a few more n-gram edge and path where you basically, instead of just tracking a single edge, you track more than one edge. So with n-gram, so with 3-gram edge coverage, you'd be tracking 3 separate edges. So you could track that you hit 3 at once, and you basically keep your tracker based on that. And with data coverage, is another interesting one that is not generally that good in practice, but with data coverage, you pretty much track which memory regions have been hit. So let's say you have a function that writes to some array, and then you write, that would be one coverage event. And then when you write to a different memory location, that's a different coverage event. So you basically track coverage based on what data you're hitting in the program instead of what code you're hitting. This tends to generally explode in terms of how much coverage you're going to be collecting. And you usually end up collecting way too much to a point where it's not relevant anymore. So it's not usually done that much. Yeah. So let's talk about why we're actually collecting this coverage in terms of coverage-guided fuzzing. So the main reason why we do fuzzing is so we can collect interesting inputs. So why we do coverage is to collect interesting inputs. So let's say we start fuzzing something, and this is basically going to be our main fuzzing loop. We have like our initial input files, then we mutate one of those files, we run the target with one of those files that we chose from our initial input files, then we get coverage feedback from the fuzzer. This tells us if this case hit anything new that was interesting. If it did hit something new interesting, we add the mutated input to our initial input files, and then we just do this loop again. So basically, whenever we find interesting case that gets new coverage, we add it to our inputs and basically expand on our sample set that we can use for future fuzz cases. And this is what we discussed for something like this, where without fuzzing, you'd have to brute force this a lot more. With fuzzing, you can see our input hit this, we add it to the initial inputs, and so on, and it makes it a lot more effective. And coverage tracking is probably the most important thing that has happened in fuzzing in the past 10 years by far. That's kind of what brought fuzzing big time on the board, made it a lot more relevant than it was before. Yeah. Any questions on this? All right, let's move on to seed scheduling then. This is usually heuristic based, and what we're referring to with this is basically how do you decide which inputs you choose. So in the fuzz loop, in this fuzz pipeline that we looked at before, we have our input files, and we say we just choose one and mutate it and send it to the target. But how do we choose one? Well, the easiest way is to just choose a random file every time and just keep running the target. So that might not always be the best. Maybe a lot of your files are super large and they take forever to run the target with. Maybe some of your fuzz cases always hidden, like maybe half of the inputs in your corpus or in your seed collection, they always hit in very early exit and don't actually get anywhere. So you have a bunch of inputs, but even though all of them have been previously marked as interesting by finding coverage or by being in your initial input files, maybe you want to prioritize some of them over the others. So that's where seed scheduling comes in. There are two main ways of this. The first one is static. So with this, you basically try to do some form of analysis on the target to determine which of your inputs are the most interesting. One of these, for example, graph centrality analysis. With this, you basically assign weights to each input depending on what this input can potentially reach. So with this, you pre-process your target and pretty much generate a graph of your target, kind of like control flow graph, for example. And then let's just make a bit of a different graph here. So let's say this is kind of our let's say this is the target we're executing potentially. Then with this type of centrality analysis, you would measure from where this input gets inside of our target, how many interesting paths are there. So if you have, for example, an input that reaches this middle part here, using coverage collection, you measure that then. Then you can see from here, this input can reach two other nodes that might potentially be interesting. We haven't found them yet, our coverage hasn't gotten there yet, but we know they're adjacent to this block, so this input has some potential. Maybe you have another input that just reaches here. And then based on your initial analysis, you can determine, well, there's nothing else I can reach from here, there's not much else here. Maybe this isn't that interesting. And based on that, you assign different weights to different cases, and you schedule some cases more than others. Another one is to determine the weights based on if the seed is on a path, like a frequently vulnerable function. For that, you would determine a few functions that you think are potentially interesting. This could be like mem copies, string copies, whatever. So any of those functions that you think might be interesting, and you mark them in this graph, and then you basically see maybe this function, let's say this might be a mem copy, and then you see, well, this is on a path to a mem copy, and this is just on a path to like two uninteresting functions. Maybe you assign this one a higher weight because it can reach a mem copy, and mem copies are frequently vulnerable. So this type of static seed scheduling is done less in practice. There has been a good bit of academia research into it, and it is interesting. But overall, it requires a good bit of like pre-processing and static analysis of your target, and that is often not what you want to do with fuzzing, because it also often makes it more expensive. So most popular fuzzers don't actually do either one of these two, but they exist. The very popular one that is pretty much done by every type of fuzzer is dynamic power scheduling. With this, you measure some properties about the input while it's executing, so you don't do any analysis on the target for this. You just measure how your input is doing while you're executing it. So with this, you assign each input a weight based on a few properties. This could be how long does the input take to execute in the target, how actually long in bytes is the input, does it get more frequent coverage increases, has it found a crash recently, and so on. So you measure a bunch of metrics like this, and then each of your cases you assign basically a weight based on those metrics, and the ones that perform better based on your metrics, you just schedule them more often. Yeah, there are also techniques like folks that use like the mutation history to decide when to stop focusing on like some edges. So let's say you have a case that always reaches this here, but it never reaches here. Maybe you've scheduled this input 100,000 times now, and you still haven't been able to make it to here. Maybe at some point you decide, okay, maybe this edge, hitting this edge is just too hard. I'm going to give up on this and focus on my other inputs. So there are a lot of heuristic-based algorithms that people do there. In the end, most of them aren't that much better than just randomly choosing an input file and running it with it. But at least the basic power scheduling is implemented in most fuzzers because there isn't really any performance detriment for it, and it works fairly well overall. Any questions on this? All right. Let's talk a bit about corpus management. So corpus is kind of the word we use when we were referring to our collection of input files while we're running. So there are a few ways how you would manage that while running, and the fuzzer does a couple of things often. One of them is corpus minimization. This kind of goes on a similar line as the seed scheduling, where you basically just try to determine which of your fuzz cases are not that great, which of your inputs are potentially less interesting than others. And maybe you find a few inputs that are very slow. Maybe they're like a massive file that triggers some massive path in the program that takes it like forever to run, or maybe it even triggers like some infinite loop, and then your target never quits. Those are inputs you don't really want in your fuzzer because they slow down your execution, and fuzzing is all about executing your target very, very fast over and over again. So with corpus minimization, you might find things like this and just delete them out of your corpus entirely while you're running. Maybe you thought it was interesting in the past at some point, but then now that you've run your fuzzer for another 4 hours, you realize, or the fuzzer realizes maybe it's not that interesting after all and just kicks it out. Another one is the initial files you choose for your input corpus are very important, and they have a massive impact on how the fuzzer is going to run. So last lecture we showed the example from the blog post that Steve showcased, where the AFL fuzzer, when it was first released, it was able to create PNG images from scratch. Well, this took a while. Like they probably ran the fuzzer for at least a day there until it started like generating decent images, and that actually made it decently far into the target, which was already amazing that coverage could do that. But one thing that's even easier is just providing a bunch of images from the get-go, and then when you just do your mutations, you're always going to have valid images for the most part. So if you provide a good initial set of inputs, you have a lot more potential to get further, and a lot faster as well. There are a couple of ways to find this initial corpus. One of them is to just go on some database that hosts a bunch of files. Let's say if you want to fuzz a PNG parser, you might find a collection of 100,000 images and just download them. Machine learning people probably know a lot of those resources where you can download large sets of data like that. This is one of them. You can also just build a web crawler, something I did at some point, just using Google's API and just download a bunch of images or whatever. There are different ways to do it, or if you want to fuzz object dump, for example, you might download a bunch of different ELF files. You might download like Ubuntu's collection or Debian's collection of just their binary files and download all of them as your initial corpus. So there are different ways to find those, but yeah. Any questions on this? Okay. Let's talk about some of the mutational strategies. So we talked about grammar-based fuzzing, where you define a grammar and it basically generates code based on that. Now we're going to just focus on the dumb mutations pretty much. There are like some things that people do, for example, like a feedback loop approach. If you see that one mutation gets new coverage more often than others, maybe you prioritize it. There's Havoc, where you just take multiple of these mutations and just choose a random subset of them and like execute them all together for one fuzz case and so on. But in general, it's like fairly straightforward. You have like these individual strategies, which like it flips, you exchange some random bytes in your target, do some simple arithmetics like adding or subtracting from certain bytes in your input. Maybe like you have some known integers that are potentially interesting, like int max or 0 or whatever, and you just inject them into random points in your program. You can change the size of your input, make it larger or smaller. You could have a dictionary of interesting strings. Those could be like weird Unicode characters, whatever that targets often fail on. You just inject those into your target at random locations. And splicing, where you just take two of your inputs and just kind of splice them together at some arbitrary location. All of these individual strategies are very simple and just do some pretty dumb mutations to your target, but they work really well overall. And then let's get to when you actually find a crash. So you run your fuzzer for a bit and you find a crash. What do you do then? Maybe I actually just demo a fuzzer real quick and might be a bit easier to look at, or just like think about how the fuzzer actually works from that. Let's start with that maybe real quick. Let's move out this real quick. So this is a very simple fuzzer that just I use as a demo for this class. It's absolutely horrible, but it gets the job done, and it's kind of easy to see exactly what it does on like kind of the bigger fuzzers that have like thousands of lines of code. You can just like look at this tiny fuzzer. In this case, written in Rust, but the language shouldn't really matter much for the small example here. We start at the main function here. We define a couple of data structures to maintain our corpus, statistics, and we read all of our input files from disk here and store them inside of the corpus pretty much. So if we look at the input files that currently exist, we have one input. And if we look at it as kind of just a very random collection of bytes. So this is our initial corpus for this fuzz case, so we read that in and store it inside of the corpus vector we allocated before. Next, we set a timer. We just do this so we can track our statistics a bit, measure how long the fuzzer's been running, how many fuzz cases per second it's doing, and so on. And I skipped a step. So at this point, we just spawn 4 threads, and for each thread, we call the worker function, and this worker function is in charge of the fuzzing. And afterwards, inside of the main thread, we just print out statistics pretty much. We start a timer, and here we just print out what the fuzzer's been doing, how many fuzz cases it's been doing, how long it's been running, and so on. Does everything make sense so far? So we just allocate some data structures, we read in our initial files, we start all the threads that do the fuzzing, and then we just print out statistics. So let's look at the actual workers here that do the fuzzing. So first this basically takes its thread ID, the corpus, and the TX just like a channel through which it sends the statistics back to the main thread, what it does. Then we start an infinite loop here. And this worker is never going to get out of this loop. It just loops on forever and keeps fuzzing the target. Inside of this loop, it then chooses a random input from our corpus, which at the beginning is just going to have one input. Then it basically chooses a random input and gets this input. And then it takes a few random bytes from this input and just replaces them with some other random bytes. That's what this line pretty much does. Generate some random bytes and replace some random bytes in this input. And then it calls the fuzz function with this input. Look at that, the fuzz function then. We create a temporary file. And then we run this program, or we create a temporary file, and then into this file we write our input. And then we just run this program that we were trying to fuzz using this input. And then we check if it crashes. If it did, we save our crash off. So this is a super simple fuzzer. That's all it does. It loads the initial corpus. It launches a bunch of threads, calls the worker with all the threads. The worker mutates an input, and then it just runs the target with this input and sees if it crashes. Does all this make sense so far on this fuzzer? There's no coverage. There's nothing interesting here pretty much. It just does a very simple random mutation, run the target with it. Now if we look at the program we're testing, this is one that was randomly generated pretty much, but it takes some arguments, basically opens the file, it reads it onto the heap, and then it calls some functions with it. And these functions, this is basically just a program meant to test fuzzers. So the functions basically just check if random arbitrary bytes in the fuzzer are equal to some other bytes, and eventually it just causes some arbitrary crashes. So this is basically a program that takes input, has a bunch of branches of function calls and whatever, and you can use it to kind of measure fuzzers. So for example, if a fuzzer has coverage collection, you might see how well the fuzzer does in like hitting all of these different functions. But for now, let's just run our fuzzer and see what it does. It's going to start running. This is where it starts printing out the statistics. When you see that it's been running for 5 seconds, it's done about 15,000 cases at this point, doing about 2,000 cases per second, and it just got its first crash. Now it has 2 crashes, and we could just leave it running, but at this point, we'll also just look at the crashes. Just another random sequence of bytes, pretty much. And now we can run the target with it. Yeah, let's give that a go. And we see that the target also crashes. So we ran the fuzzer for like 10 seconds and it found like 2 inputs that crashed the target already. So this is the basic fuzzing loop at a very basic level. Just a very simple toy example. Real fuzzers then have coverage collections. They have seed scheduling algorithms to determine what seeds to choose and so on. But this is the basic idea of a fuzzer pretty much. Any questions on this? All right. Does anyone want to have an idea of, so we have this crash now. How would you go about trying to determine how this actually crashed, right? Your goal is not to just find crashes, you want to report the bug to the software developers. What do you tell them? You could just send them the crashing input and tell them to deal with it, or you actually, at this point, do crash triaging and kind of try to figure out how exactly it crashed and try to give a more appropriate response where you tell them where exactly the bug happened. Or if you want to write an exploit, you also need to figure out how exactly the bug happened. Just having a crash is not enough. So what could you do at this point to figure out where the crash happened?
You could run the binary with that input in GDB and just step through it and see where the crash happens.
Yeah, sure. Let's do one better and actually recompile with debug flags first of all. Just to make sure it still crashes with the input. And it does. So we just launch the same test program that caused the crash, and then we run it with the file. And we see we sec faulted at line 518 because our condition was met. So this is kind of what you're going to be doing in Project 5 as well for 2 of the challenges. You're going to be using a real fuzzer though, being AFL++, and you're going to be fuzzing a real target, being object dump. A very old version of object dump, like 2014, that has a bunch of bugs. But for Project 5, you're actually looking at some real software prawns. So what you're going to be doing is you're going to be fuzzing it, and then you need to figure out where the crashes occurred, figure out why they occurred, and fix the bug in object dump. So for this crash triaging project, the first step you can do is just run it using GDB and see where exactly it crashes. So at this point, we found this crash. We could start going backwards from here and try to determine how exactly we reached this point, and then recreate it in potentially a more minimalistic example. But yeah, so that's the most straightforward way of doing crash triaging. Little standard debugging. So you just load into GDB and you try to determine the root case of it. There are some other debuggers that you can use to make this a little more comfortable sometimes, being timeless debuggers or like time travel debuggers, whatever you want to call them, that let you step backwards through code. GDB can't do it, but there are some debuggers that can. For those, once you have this crash, you can not only step forward by which in this case you can't really do, but you could also start stepping backwards and basically go backwards through the code and see where exactly you start corrupting memory. In the very last lecture of the course, we might introduce one of those if we have time. They're pretty interesting, but yeah, so that's one of the ways. The general goal is just root cause, either through normal debugger or this. There's also crash exploration. This is a more automated mode that a lot of fuzzers like AFL also support. with this, you just give the fuzzer a crashing seed as its input, and you put it into this crash exploration mode. And it's basically just going to run the target with this input and try to generate a lot more inputs that cause a very similar crash. So why would you do that? So from this, you're going to end up with a bunch of crashes that crash on the same code snippet, most likely. So at that point, you could, in theory, do statistical analysis on this to determine how the crash occurred just from having a bunch of samples. So you might have like 10,000 samples that all cause the exact same crash. And then using statistical analysis on all those samples, you could say, okay, this crash only occurs if the input is of length above 300, and maybe if input of 30 needs to be 0x41 or whatever. Because you have all these samples, and you can kind of compare which conditions need to be common between those samples for the crash to occur. So that's one of the modes that that AFL, for example, has. Another way of doing basically the exact opposite is to dedupe crashes, where you group similar crashes together. Let's say your fuzzer spits out like 100 different crashes. Chances are they're not all for different bugs. Some of them might be the same bug. So you might just like run it, and based on coverage, you can determine do they refer to the same bug or different ones. And then you basically remove all the ones that are similar, so you can focus on a smaller subset of the bugs instead of having like those 300 crashes in front of you. Any questions on this? All right. So let's get to harnessing. This is what you're going to be doing for project 5 challenge 3. So a lot of targets, we've talked about a couple of very simple targets so far, like object dump, image parsers, whatever. They just take a file and they parse it. So you're running your fuzzer is very easy. You just run your target through the fuzzer, and you provide it like the fuzzer just provides the file, and it's going to fuzz it. But there are a lot of targets that aren't that easy to fuzz. For example, you take something that takes network protocols. You can't just give it a file and expect it to work. You need to send it network protocol somehow. So this is where harnessing comes in. This is where you basically enwrap your target in a harness that is the executor for it. So if your target takes, let's say it takes these network packets, one thing you could do is you write a test program. Say this is your test program, and you run your fuzzer, let's say AFL, with this test program, and this test program basically just gets you random files from AFL. So say this is the fuzzer, it's the harness, and this is the target you want to fuzz. So then the fuzzer is going to give you a random input to your harness, and then what your harness can do is it can pretty much take this randomly generated input from the fuzzer, and it can, instead of just writing it to a file or whatever, it can set up like some socket connection with the target and send them over as HTTP packets. So it maybe just inserts the data that the fuzzer generated inside of valid HTTP packets and sends it to the target. That's something you can do. Or you're dealing with some embedded device that maybe you can't launch as you can't put your fuzzer onto the embedded device, like a small router or whatever. So you need some other way. So maybe you get the firmware off the device, you emulate it, and then your harness just writes it straight into the target's memory space or whatever. There are a lot of techniques in that space of how you harness the target. Or the simplest way is maybe it's just a library. So you can't just run the target, but you need to invoke the library. So in your harness, you just call the target's library functions using the randomly generated input. So basically just doing whatever you have to do to give the target the input, your randomly generated input, in ways that it accepts it. Sometimes it's very easy, just give it a file. Other times it gets a lot harder. So if you're going to be doing fuzzing, for example, for your presentation, some targets that you chose, I think one group has like a PDF parser, for example. That's very easy. You can just give it PDF files, do random mutations, give it the file, and it's going to run it. Other teams have something more complicated, like Amy's group, for example, has a game client, and the game client's going to expect its data in terms of like input packets. So you need to put more work into actually harnessing your target for that so you can send the packets to it. Questions on harnessing? Yeah.
So how is this different from like grammar-based fuzzing?
So the grammar and mutational-based fuzzing is just based on how you generate the input. With harnessing, we're more referring to how you actually feed this input to the target. So with grammar, you would say, let's say you have like some compiler and then you define a grammar to generate valid C code or whatever. That's what your grammar part does. That's like all of this happens inside of the fuzzer and you generate some test case. And then the harnessing is pretty much how you then give this test case to the target so it actually runs it. Yeah. Any other questions? All right. Let's move on to, this is already the last slide of fuzzing, so it's actually went pretty fast today then. Let's talk a bit about the performance of fuzzers. So this is very important because with fuzzing, you're basically trying to run a target over and over again, and how fast your fuzzer executes becomes very important. Say you have a slow fuzzer might only execute a target 10 to 20 times per second, then you have a faster fuzzer that executes it maybe 10,000 times a second, and that's a massive difference. This is why a lot of the techniques that academia has researched, especially based on like machine learning or NLP, whatever, there are a lot of very interesting techniques in that field, but a lot of those slow down the fuzzer by orders of magnitude that make it worse overall. So even though the fuzzer chooses smarter inputs, does smarter mutations, does everything better, it just does it so much slower that it ends up being worse. So performance is very relevant. There are a couple of things that fuzzers do. The first one is in-memory fuzzing. So in the example fuzzer that I demoed earlier, we wrote the files to disk and we ran the target with those files. This is not very fast though, because writing to disk, we need to invoke a syscall, we need to hit disk, all of those, that takes time, and then we start the target using that. So this takes a lot of time. So another approach to that is to just keep your corpse entirely in memory. So if we look back at the target from earlier, in this case, the target has like the main function and just reads a file from disk. Well, we have the source code to the target. What if we just slightly modify the target, for example, and instead of reading the file from disk, we just make this a callable function, and instead of taking its input from disk, it just takes it as an argument. That wouldn't be very hard to do. It'd probably be like less than 5 minutes of work to make that change. And suddenly your fuzzer can just run the target and pass the input right in memory instead of having to write it to disk and have this thing read it from disk. If we look at AFL, for example, it has some automated ways of doing this. It's not fully automated. You still need to like slightly modify the source code, but not like entirely. And then it just does everything in memory. And this basic generally has like at least a 2x performance increase. Oftentimes even goes up to like 10x. And that makes it a lot faster and is very important. Another very important part is actually scaling your fuzzer. So the fuzzer I ran earlier, I ran it on like a small 4-core laptop. That's not how fuzzing is done in the real world. Usually, if you're doing fuzzing, you have big servers with hundreds of cores, and you fuzz big targets for days on end. So that's where scaling becomes a very big issue. You can't just make sure your fuzzer runs well on one core. You need to make sure that it also runs well on all of the cores, pretty much. So we talked about a lot of like the data structures that are involved in fuzzing, be it like the coverage map, the corpus. All of these are shared between threads. So when you're doing fuzzing, you also need to be careful that you don't put too much information that you share between threads, and that allows it to then basically scale a lot better. Optimally, if you have one core, it executes 50 plus Ks per second. If you add another core, it just doubles it. That's what you'd optimally want. And usually that doesn't really happen. But at least until like 30 cores, a lot of fuzzers do get very good performance. And then when you go up from 30 cores, the scaling often slows down, especially for fuzzers like AFL++, which is unfortunate. Could be going a lot faster, but it doesn't, but it is what it is. A lot of it is because another thing that greatly impacts the scaling is also just having syscalls inside of your fuzzing loop. So the issues with syscalls is you have your operating system, and whenever you do a syscall, it hits the kernel. So let's say you have 30 threads running your target, and all of these do like the same syscalls hitting the kernel. If you start actually looking at kernel code, you'll see that since everything has to be able to be run on multiple threads, there are locks everywhere. So if you have 30 threads hitting over and over the very similar set of syscalls, they're going to start getting stuck in all of those locks in the kernel forever. And then when you start actually running a fuzzer, you'll see that you spend like half your time just sitting in the kernel waiting for locks to resolve instead of actually doing fuzzing. And this is what happens pretty much most fuzzers that you're going to be finding in the public space. If you use AFL and you run with like 50 cores, you'll see that you spend like 60% of your execution time just sitting in the kernel waiting for locks. And that is not something that can be avoided with a general model of how these fuzzers work, but it is a pretty big issue. That's kind of, for example, like another reason why you do this in-memory fuzzing. You don't have to hit disk, and you don't need to go into the kernel for that. You just pass in a memory buffer. And then there's something that's a little bit more complicated, being snapshot fuzzing. Before we go into that, do you guys have any questions on in-memory fuzzing or scaling the fuzzer out? I like a large scale. If you look at, you don't just scale it on one machine as well. You also kind of want to distribute it between different machines. This kind of goes into like the distributed systems realm, where you want to have all your machines coordinating together and sharing their fuzz cases, but still performing well. So that's another thing you consider when you talk about scaling, where Google, for example, they're fuzzing Chrome like 10,000 cores. Those cores are all spread out through a bunch of servers, but you still want to have the servers communicate their like corpus, their coverage, and so on. So there's a lot of things that go into like making a fuzzer scale well. And that's why a lot of fuzzers don't, unfortunately. But yeah, then there's snapshot fuzzing. This is something that's very interesting, but it requires generally a good bit more manual effort. With this, your goal is pretty much to just fuzz in a short loop around target functions, and then you can base future cases off of that. Let's explain this a bit more. So let's say you have your target. Let's draw a control flow graph again, whatever. Let's say this is your target. And let's say this is the interesting function that you think might have some bug. Maybe this is a function that like does some complicated parsing, it leads to a bunch of other functions, whatever. You think that a bug might lie here. And after this region, you might have like some exit calls, some uninteresting code that you don't care about anymore. Maybe like here it does like its calculations and then just prints out the outputs. So maybe you don't really care about this initialization and this finishing that much. You just want to focus on this one part that does the interesting calculations that is prone to have like some form bug. Maybe like this is what parses your file format. So the code at the beginning and the code at the end, it tends to be pretty expensive. Like if you're printing, let's say this like starts printing out statistics for whatever, or like you run object dump and this is where it prints out all the data to the screen. Printing out data also requires syscalls and it's expensive. So what if you can just avoid this and avoid all the initialization and focus entirely on this? So this is where snapshot fuzzing comes in. So with snapshot fuzzing, you basically take a screenshot of the process at this location after it has done executing this. Then you run your target. And once you get to this point, you can measure this based on coverage. Once you hit this point where the interesting part is over, you just change your entire state back to where it was before. And then you redo it. So how could this look in practice? All right, so let's start with how you get to the first step. So you know where you want to be, and you want to just get your targets processed, your entire memory, your registers, all of it. You need to save off once you get to this space. The simplest way to do it is to just use a GDB script. So GDB also has an API. You can script it. So in this case, we have a pretty simple script that. Let's see, where's the start? That once invoked, zoom in a bit maybe. So once invoked, it pretty much just, so you run your target in GDB, you set a breakpoint on this location where you want to take your snapshot, and then you can invoke a script like this that basically just dumps all of memory. Those scripts also exist for WinDebug, GDB, whatever. This is one that I wrote a while ago. But pretty much So for example, you get all the process mappings in some way or another through the GDB API, and then you can parse all of them out and just dump them all to disk. So in this case, we parse out all the data that's currently mapped in the process memory space. We get start, end, size, offset permissions, and the actual raw data, and we dump all of that to disk. We do the exact same with like the registers. We dump them, and we dump like the open files. All of this basically just dumped to disk. And what this does is that basically, once we get to this location, we set a breakpoint GDB, and we dump all of this to disk. And then we can start running our fuzzer at this point. We tell our fuzzer that this is where the interesting part stops. And what the fuzzer can then do is it runs the target, and once it hits this point, it just resets the entire memory state of the target to this initial space that you saved off earlier. So why is this a bit more complicated than normal fuzzing? Or more involved at least. First of all, you need to generate this initial dump. If you have a target that you can easily run, this is not that bad. You can just run your target in GDB, set a breakpoint, and just dump out the entire memory space. Against some other targets, it's harder. If you have, for example, an embedded device or a phone or whatever, you can't very easily just debug the entire thing using GDB or whatever that easily and just dump all of memory. So that's already something that makes it a lot harder for a lot of targets. But if it's a simple target that you can just run, this part is not that bad. Next, you need to instrument how you actually want to pass your test case to the target. So with the test case we've done so far, maybe just reads a file from disk or whatever. In this case, maybe set your breakpoint at a point that's after where it read in your test case. So what you do in this case, maybe you have a function. So this might be your function signature pretty much, where it takes the input as like a car pointer and then the size. So let's say you set a breakpoint and you dump the memory space right at this location when this function is first called. Does anyone want to have an idea of how you could still give it the input at this point? If you have full control over the target's memory space. Maybe you're running it in an emulator at this point, something like that. What could you do at this location then? So you know that this is how the target function is being executed, or like it's how it has to be called, and you're right at this call. So you're at the first instruction of the function. And assuming you want to fuzz this input variable here, how could you do this assuming you have full control over the target's memory space?
Change the registers that are passing the arguments into the thing.
Yeah, exactly. So in this case, you know that the first argument is an RDI, the second one an RSI. So what you can do is just you take the pointer of RDI, and wherever RDI points to, you write in your input into this location. So you have RDI, you see where it points to, and you just write your input there. And RSI, you can then just overwrite with the size of your input. So at this point, you then successfully set up your input, and then you just let the target run until it's there. And at that point, you can then reset back to this state and do the exact same thing again. You take the input, write it into its memory space, and keep executing. So this is a more advanced fuzzing technique that for a lot of targets is kind of required though. So for this, this often comes in when you're dealing with embedded targets, for example, that you can't easily run, that you run in an emulator, or when you have like some big GUI application. Let's say you want to fuzz some video game or whatever. It has a giant GUI, and if you were fuzzing it normally and just launching it from scratch every time, you'd have to wait for the entire GUI to launch before you can start fuzzing it. With snapshot fuzzing, you can set a breakpoint. You let the GUI launch once, so it's massive, like all the windows are drawn and whatever. You set a breakpoint after all of that has happened, and then you can send it your inputs and just reset it back to the initial state by just resetting the memory state, and you never need to like relaunch all those windows and whatever. And it makes it a lot more efficient by a massive margin. This is a more advanced fuzzing technique where you can't just like point a fuzzer at it and tell it to run. We need to like actually do a good bit of manual work for it, but it's extremely effective. There are a couple of fuzzers that work like this. I've written two because I think it's a very interesting field. There's one called WTF, What the Fuzz, that's mainly a Windows one. There's Nix, which is based on hypervisors. If you're interested in doing that for your project, you can come talk to me. I can give you some resource on like how to do it. But it's a very interesting technique that's extremely effective. but a little bit more advanced in the fuzzing space. Any questions on this? I think we might also be doing a demo of snapshot fuzzing in the last lecture. I think you wanted to do that, or at least time was. We'll see.
If I can get it working.
We'll see. All right. Any questions on fuzzing in general? Because I think that was our last slide for that. All right, then at this point, I want to announce an extra credit assignment. So this is not very much of an official assignment where we give you an assignment. This kind of, you choose something you want to do in the realm of the course, and you kind of make a proposal to us for it that you want to do that, and we're probably going to say it's fine, and you can get a couple of extra credit points for it, depending on what it is. This is not meant to be like the same as your presentation where you like choose some target and do the R on it. It's kind of just expanding on like some small skill that we did in the course. So for example, you could be learning a new ROP technique, you could be learning a new house heap technique, you could look into kernel exploitation or anything of that sort, or maybe like program analysis. We're going to talk about something after like this announcement. I'm going to like introduce a different tool. You could write something with that. So like something which covered in the course, like go a little bit beyond that and learn a bit more about it. And yeah, that's pretty much the entire assignment. You just tell us what you want to do and we'll probably approve it, either good in person or CamSmart or whatever. If you don't want to do it, if you're already busy, just completely ignore it. If you have something that you're interested in, you can get a few extra points for that. Any questions on that? And if you like want topic suggestions or whatever in some realm, you can also just ask us about that and we can give you some suggestions of what you could be doing there. All right, so for the rest of the lecture today, the topic is going to be very unofficial then, something that wasn't on the syllabus yet, because we're still pretty much ahead by like half a lecture, and I don't really want to start on the next proper topic now because we've kind of been in a pattern where I like get through half a topic and then like need to do the rest of the half in the next lecture, and that's kind of annoying. So let's just today finish with like a different topic a bit, and then tomorrow we start on the next syllabus topic. So for this, I want to introduce a tool that I actually just found out about 3 days ago. And has anyone heard of CodeQL, first of all? A couple of people. So CodeQL is a tool released. This is not the tool I'm going to be talking about today, but I'm going to talk about something related. So I'm just going to talk about this one real quick first because it's a lot more popular. So CodeQL is a tool that is released by GitHub, developed by GitHub. They bought up a different company that did it first, and like they've been developing it since. And it's basically a cool tool to statically analyze a code base. So what it does is you basically give it a target. So like could be like some open source repository. So you point it at this target, and it's going to take this target and parse it out into a database. So this entire target, like all of the functions, basically all of the code from the source code is just going to parse into a database. It's going to do that by trying to compile the target and, yeah, question?
Is that the AST analyzer based on tree sitter? Or?
I'm not sure if it's based on tree sitter. It might be. Very likely, I guess, but I'm not 100% sure. Yeah, it does something in the background. I'm not 100% familiar with it, but it basically parses it into a database. And at this point, it lets you query the database. And I can open up like an example of it real quick. It's a tool that GitHub has been pushing really hard, where you can basically register CodeQL actions as like actions on your GitHub repo that like run automatically. And it's basically a bunch of queries that analyze your code and try to find bugs in it. So CodeQL comes with a bunch of default queries that, for example, check for format string bugs or for some form of command injections, whatever. And you can basically register that as an action for your GitHub repo, and a lot of companies have been doing that. And it does a lot of those checks automatically. They're far from perfect. There's a lot it can't find. But this is kind of how the syntax of CodeQL looks. It's very similar to how SQL would look. Right from this, so where, whatever, select this stuff. And you can basically do that to like analyze code. One major drawback of CodeQL though is that the code needs to be compilable. So CodeQL parses code. A big part of it is based on like actually being able to compile the code, where it hooks all the compiler outputs, it sees what files the compiler is compiling, and it retrieves all of that. So that's kind of a downside. Your target actually needs to be compilable to run CodeQL, and CodeQL also has licenses where you can only use it if your target is free and open source. So if you're like at a vulnerability research company, you can't really just use CodeQL to audit closed source code from like your clients. So this is where the different tool comes in that I want to introduce here. It's called Urine. It's being developed since like 8 years now. I'm very surprised it's like the first time hearing of it. But it has a very similar purpose of CodeQL. You basically give it a code base, it parses it out into a database, and then you can run queries on it. Another thing I like about Urine is that instead of being based on this SQL-like query, it's based on Scala, which makes it a lot more comfortable. Let's look at how this tool actually looks and why it's so interesting to us. So we're going to be looking at, let's start with this code. This is just like a slightly modified version of one of your projects. It calls have like a malloc. If you remember, there was like a printout format string bug here. I added like some other vulnerable functions here where it does like some allocation and then like calls fgets on it and so on. I added just like some extra bugs on it, but this is a pretty buggy program overall. So what we can do using this tool, we can basically just tell it to parse the directory, like the files in this directory, and so run. And now it's going to just run real quick, and it's going to parse the code, and it's going to save it to like the database. This database in this case is the cpg.bin. Just look at what files are in there. I guess just okay. It's not that we can actually look at. But now let's start running it against it. It's going to take a second to actually load the database. Once it does, we have this nice REPL here, and we can start interacting with the database. So Urine is based on parsing everything into a graph format. They call this format the code property graph, and it's basically a format that combines a control flow graph, an abstract syntax tree, and a dependency graph all together. And this, you can do all your analysis based on this graph. So you have this graph of your entire code base. So you can, for example, you take this graph and you can look at all the methods for it. You can just do this. Function. And this now just printed out all the methods that are being called inside of this function, or inside of this entire program. Maybe we only care about the ones that are internal to the program, the user define themselves. Maybe we don't care about the malloc function or the string CSPN function, some of these functions. So we can start like applying normal like program structures on it, like filters, stuff like that. So we can. So one of the constructs is the where not, basically like a filter. Not sure why this isn't working right now. Live demos. The idea behind this was to like basically look at the ones that aren't external, but in this case it didn't really work. Let's move on from the live demo real quick and just look at a different, like at an actual query real quick. But you can query this graph, so we can look at all the methods that it has, we can start filtering through it and start parsing through it. So what I did yesterday with this was to basically write a small tool based on it. A little bit, maybe make it more readable. So this, if you were at the Tull workshop a few weeks ago, he demonstrated a little tool that just maps sources to things using a scripting API with decompiler. So we're doing the same thing based on source code here, pretty much. So I defined a bunch of sources like malloc, calloc, realloc, a bunch of functions that allocate a buffer, and to this we also allocate a bunch of, determine a bunch of things that maybe when acting on a buffer could expose a vulnerability, like memcopy, memmove, string copy, whatever. Then we're going to loop through all of these sources and all of this things and call the source sync mappings function on that. And if you've ever written Scala before, you probably hate this code because I haven't until 2 days ago. It's the first time I've looked at the language, so this code was probably horrible, but it kind of worked. So I'm just going to introduce this real quick. So this basically does the API of this tool, Yearn, has data flow analysis inbuilt. So we can basically say that we just want to look for the sinks that are, so from these sinks, we want to look at them where like data travels, like some argument, or the argument returned by malloc, somehow ends up inside of this string copy, or one of these like sinks. So we can say, we'll look for the sinks that are reachable by one of the sources, or the source that is passed in here, and we just do some filtering on it to like return it in a nice way. And this function basically uses the Yearn API to return all of the mappings where one of those sources maps to one of those things, where data from allocated by malloc is passed to one of those functions. And yeah, that's just going to print that out for us for the most part. So let's say let's run it against the database we generated earlier. Let's open this up again real quick. All right, so just running the code now, and just finish already. We scroll up, we can see that it found a couple of things. So from the project, it says that on line 54, there's a malloc call, and the argument of this is then passed to an fgets call on line 18. This is not actually telling us that there's a bug, it doesn't know that. At least from what we scripted out, we could make it smarter and like write more to it. We're just saying like this is where we allocate a buffer and it's then passed to a function that's potentially vulnerable. The exact same thing is happening here. And if we actually look at the code, we would see that yes, there is in fact a vulnerability because we're mallocing a size of 50 and fgets a size of 299. Same with those two. Another thing that we could do is we could once again look at the methods that the program has. And one of the bugs we covered was format string bugs. So let's say we want to automatically find format string bugs. So we can first of all find the methods that are called printf. And then at this point, we can start filtering that as well. All right, I do not want to do this live coding right now because I'm not super familiar, so I'm just going to open up my notes on this, where I actually wrote that down. All right, so let's look at the query real quick here. So we look for all the methods of printf. We look where it's calls printf, and then we check where the first are. So we look at the arguments, and we look where the first argument is not a literal. So we're calling printf, and we want it to be safe. Remember, like our format string bugs, they basically have like a printf, for example, and then the first bug was like some variable, for example. This is what's potentially risky. So what you want is for it to be like a string literal, for example. So this query, all it does pretty much is it looks for all printf calls where the first argument is not a string literal. So we can run this, and it's going to tell us that inside of the code, there is a call where it just printfs with some buffer instead of a literal. So we can tell it to like dump the code in this area, and we can see that inside of this, into this play function, a name is passed in, and this name is then just printed out using a printf, and there we have a potential format string bug. So we have a small program like this that we can just quickly look through and read the code for. This might not be relevant. We could have found this very quickly ourselves. But the nice thing is that this tool also works against massive code bases. You could have like a code with like 100,000 lines of code. You could run this, and you could very easily find like some low-hanging printf format string bugs or something like that. More importantly, with, for example, the earlier thing where you can map things to sources, maybe not all of them are going to be bugs, but it can give you like some things to explore. So Let's look at a more interesting example now. In this case, looking at actual targets being readelf. Many of you have probably used it. It's one of the standard Linux utilities. So I kind of learned a bit about an elf file. So I already generated the database for this before the lecture, the binutils database here. So with this, I basically downloaded the source code for binutils and then had Jorn parse out the entire thing. So then let's once again let's copy paste the tool in again the thing that from earlier, where that basically maps out all the source to sinks. So in this case, it's going to take a bit longer because it needs to parse the entirety of the fgets of binutils. Had some bugs here. The tool is not perfect, unfortunately. But it also found some potentially interesting things. Let's look up what those were. Okay, so it gave us two things where it says potential heap vulnerability, where it basically had mappings from some form of malloc call to then a memcopy. Here's another one, malloc to memcopy. Keep looking down. I don't remember having this many issues last time I ran this. That's unfortunate. Okay. Okay, let's just start, let's close it out here, I think. Okay. All right, so it gave us a bunch of source sink mappings. It also had a bunch of errors. I'm not sure what they were from at this point. Could look at the tool for that. But let's look at actually one of those bugs and look how you might actually triage them. So let's start looking at this one. This is one of the ones in output, and it does an allocation inside of readelf.c, line 2600, does a calloc of section +1, and then does a memcopy in it. Why would we potentially choose this? Well, there's the section +1 that it does the allocation with. That sounds like it might have an integer overflow bug. So let's actually look at this. So open up readelf.c, go to the line that it told us about, and here we have our allocation, where it does an allocation of section +1, and I actually already added some debug prints here because that's the code I was looking at yesterday for using this. And if we look down a little bit at this point, we can see that here it does the memcopy, where based on this allocation, it does a memcopy into this. So in this case, if from this, we can already say, if we can pass a section variable in here that is integer max, and then it adds 1 to it, it's going to have integer overflow, and we're going to have a tiny heap allocation. So this has potential to be a bug, for example. Just based on running this tool and quickly looking at this, this could be interesting. So what we can do at this point, we can look at where this is called. So this is the request dump function. So we can script this out. We can say, so first of all, we can list the method, and then we can look at all the callers, and look at the names of those. Now we can see that these are the functions that actually call this function. So and then let's also print out the, instead of the name, let's just print out the line number. That's not looking great. Okay, but you could then get the exact location of where it's being called using this. I'm not good at demoing this right now. Yeah, let's just find out where it's being called. In this case, one of the locations where it's called is if you execute readelf with the X flag, you can then, it parses out the section from your arguments, and then it calls request dump using the section you pass with the arguments. So this could, in theory, So if you can pass as an argument int max, you might have a heap overflow here. So we can actually just test this out. So if we run it using the x flag, run it against some arbitrary binary, -x. The printouts are going to happen. It's going to tell us the section is of 123. That's what we passed in as arguments here. And the allocation size is going to be 123 plus 1, the 124. So if we then determine what int max would be, could try sending this as an x. And if this would behave as we would expect it might have had a massive section of the massive value and then allocation size of 1. Unfortunately, in this case, it doesn't work because of this section is unsigned integer, and then it has like this check here. So it doesn't quite have a bug in this case, but it's very close. And you can use these types of static analysis tools to very quickly go through code and find like locations where it might be interesting parts like this. I'm not sure, this was probably not a great explanation of this tool, but I would encourage you to look into it, especially if you were looking at some open source target for your presentation. You can use this to basically run queries on your code and look for a lot of different code patterns that might be vulnerable. Yeah. Any questions on this? All right. Let's end 5 minutes early then. It's just kind of a little bit of an extra thing. There's not going to be in any of your projects or whatever, but this is a very interesting tool that I was not able to demo very well here today, but I would encourage you to check it out and play around with it a bit because it's extremely powerful for a lot of things, and you can use it to help your presentation process a lot if you're dealing with open source code.